Hey gang, Vespa here, coming into week 3, right? So what do we have to expect for this week? Please remember, tomorrow, Monday evening, quiz 1 is due. Still calling it quiz 1, even though it's our only quiz for the summer. Normally, I would have my class do quiz 1 over unit 1, and then quiz 2 would cover unit 3. But this is your only quiz this semester, but it's worth 50 points. Please take it seriously. Remember, you have 3 attempts on it. Okay, it's going to cover chapters 1, 2, 3, and 5. That's our unit 1. Okay, so you have 3 attempts, so please take it seriously. The whole point of the quiz is you have all these helps on the homework that help you get through it, which is good. They help you learn it, give you the immediate feedback, right? But if you rely on those just to get a good grade on your homework, you're not ready to recognize a problem on its own, figure out what process to use, and then execute the process properly, right? When I know I'm working in the 3.1 homework, I know I'm doing measures of center, I'm doing mean, medians, and modes, right? So it's easy to know what process I'm using. But come quiz time, come test time, you have to read a problem and then recognize what it's asking of you, know how to pick what process to use, and then execute the process properly, right? Those are the big 3 steps in problem recognition and solving. And so we need to practice that, right? You need to practice the problem recognition outside of knowing I'm working on section 5.2. That's what the quiz is. It's a bridge between the homework and the test. Okay, so I'm trying to give you an opportunity to recognize where you're at in terms of that problem recognition is. So please please take the quiz seriously here. It's not meant to hurt your grade. It's meant to help it with the 3 attempts, right? But also to help you bridge between doing homework and being ready for a midterm exam, right? So that's due Monday evening. And then after that, you're going to work chapter 4. In chapter 4, we're working with bivariate data. Okay, it's different from what you've seen so far. So far, your data has been just lists of, qualitative characteristic or a quantitative value, and so it's just been like the heights of 50 adult American females or something like that, right? Where each data value is just a single numeric value, but bivariate data carries 2 pieces of data with it, right? And so analysis of bivariate data is a little bit different, and we're going to do an introduction to that in chapter 4. Okay, so please see this next section to get a little quick visual on what that's about. Previously, so far, we have worked with univariate data, which carries with it a single piece of information. And if that information is numeric, then each data point carries a single piece of information, and all of those data values could be plotted on a number line because they only carry 1 piece of information. Bivariate data differs from this by carrying 2 pieces of information. And if those pieces of information are numeric in nature, we have the independent variable and we have the dependent variable. And they're referred to that because one can be chosen independently and the other depends on that. And if there's a strong correlational relationship there, then the independent variable could predict, right, or explain the value of the dependent variable. Now, bivariate data, because it carries 2 pieces of information, could be graphed. Now, it doesn't have to be strictly in the first quadrant, but I'm going to draw it that way for now, right? Can be plotted in the coordinate plane, okay? And now the relationship between x and y can be many, many different things, right? There could be no relationship at all. Sometimes it could be linear, sometimes it could be quadratic, it could be many things, but we like linear relationships because they're simple, right? Now I've drawn kind of a scatter plot here, and you can see it's somewhat linear in its relationship, that there's this line, right, fairly well follows the data. And that's something we're interested in, is can we draw a line that well represents the data? And we like that for a couple of different reasons. You know what, actually let me modify this drawing real quick. So one of the main reasons we like lines is because the rate of change is constant. Okay, and what do I mean by rate of change? The slope, right, which is simply the ratio of the change in y over a period to that change in x over that same period. So we're talking about an interval of the change in x versus an interval of the change in y. And that rate is constant regardless of the interval I choose. If I go instead with this interval, right? If I draw that a little better, okay? You can see those triangles are similar, which means the ratio of this side to this side is the same as on the bigger triangle, okay? Which means the slope stays constant, and that ratio, right, we use by m to represent it, is the change in y to the change in x, okay? And that is constant for a line, and we like that because it's easy. And another thing we like about it is a line is uniquely identifiable by its slope and another characteristic called the y-intercept, okay? And that's the height from the x-axis at which the line crosses the y-axis. And those two things are unique to a particular line, right? So if we can find this y-intercept and the slope, we can write an equation for a line. Now that's helpful if I jump back to the first slide. Right, say I wanted to know what the value of y would be for this x. Well, I don't have a data point there. But if a line very well represented this data set, right, then I could use the value of y on the line right there. Maybe I'll draw that in red to jump out at you. Right, I could use the value of y on that line to predict what the value of y would be for this value of x. And that's very, very helpful if we have good linear models for things. And that's what Chapter 2 is all about. So, excuse me, not Chapter 2, Chapter 4. Now this may seem like simple, silly algebra to you, and x's and y's, and you think this stuff is arbitrary and meaningless, but believe it or not, linear models are one of the most important thing in all of mathematics. And in modern day even, your electromechanical devices don't operate well without linear models. In fact, we love linear models because of their simplicity, and for many, many years before computers were super fast, they couldn't keep up with more complex models. So this is really important stuff, and this society and our devices don't work the way that they do without this form of modeling. So while you may not use it all the time, I certainly understand that, but this is a very, very important concept in mathematics, believe it or not.